Hello, everyone, and welcome back to the 2018 Hack Summit. We're joined today by Quaintance and Stuart Popejoy from Cadena, and Cadena streamlines blockchain for businesses. They have the first smart contracts that are human-readable using a language called Pact, and their blockchain features scalability, security, and speed, and they've innovated and created something called ChainWeb, which is a massively parallel protocol, and they're going to be educating us on a variety of technical subjects today. So it should be great for the engineering audience here to learn all about this. And Monica and Stuart, it's a pleasure to have you. Feel free to take it away.
Thank you.
Thanks, Ed. Stu, you want to go just talk about yourself for like 30 seconds?
Yeah, I'll just quickly introduce myself. I'm one of the co-founders of Cadena. Me and my partner, Will Martino, founded this company in 2016, and we're really thrilled to talk to you today about consensus protocols. That's what Monica's going to be discussing. I'm going to be talking about the Pact smart contract language and kind of advanced issues in smart contracts.
Cool. All right, I'll see if I can start my screencast.
I'm going to mute my video.
Did that work?
Video, I'll mute mine as well. That way it focuses on her.
Yep.
All right, I did Perfect. It. Can you guys see my slides?
Slides are there.
Sweet. Okay, great. So this talk is geared towards either interested engineers that are new to blockchain, or maybe people that have spent time on the application development side but haven't really thought very deeply in terms of consensus protocols. And there's actually a pretty long and interesting history to how we ended up where we are today in terms of all of these many consensus protocols that we've got. And I want to go through a little bit of history and context so that when people say like, oh, this is DPoS, or like, oh, this is federated, you'll know what that means. Because there's a whole lot of projects out there doing a whole lot of stuff, and sometimes it's hard to, you can't really tell them apart. So let's just jump into it. So just in case you're like, oh, you didn't talk about my favorite project, I'm going to tell you the things I'm not going to talk about. He're not going to talk about second layer scalability solutions. So we're not going to talk about Cosmos or Lightning or Thunderella or Solana. If you want to hear about Thunderella, like stay tuned to Latency is coming up in a few hours. And we're not going to talk about DAGs because they're like a whole different type of way of coming to consensus in terms of ordering your ledger. So IOTA, Hashgraph, NEM, we're not going to talk about them today. So I am the head of public development at Cadena. I worked on ChainWeb paper with Stu and Will, and I used to work at the SEC briefly as a quant, as a systems engineer, and had a career as an opera singer. So, all right, let's jump into it. Work is what we're doing and the work that people are currently doing in order to push the envelope of consensus protocols in public. So what is consensus and why do we care? So the idea is that when, imagine the 1960s, 1970s, you have one computer. Now you want to make one computer talk to another computer. Now you have to have two computers, maybe three computers, and they all have to agree with the state of the world. You can't have consensus between three things if they all think about things differently, if they all have a different record of information. So this idea of having computers that can talk to each other and robustly understand how to resolve conflicts is called fault tolerance. So we care about fault tolerance. Like imagine the first ever time when you had lots of sensors all trying to talk to each other, aircraft microprocessors. So you had a processor in the nose and two in the wings and one in the tail, and the one in the nose and the wings are all saying, the system is fine, and the tail is saying, we're going down, we're going down. So you would want to disregard the signal from the tail, but then maybe when you have more than the sensors, maybe more than 51% of the sensors saying something is wrong, then you might want to start listening to them. This idea is the 2 points you would care about is safety. So everybody agrees on a consistent log. There's nobody that can have issues with having a false record or trying to cheat the system. And you need to have liveness, which is the idea that you're going to come to consensus, that you're going to proceed forward in some point of time, and it's not going to take you forever to do so. Historically, we had aircraft microprocessors, and we had to figure out how to make them talk to each other. So this brings up the Byzantine generals problem. If you saw, I think one of the Hashgraph guys talked about Byzantine fault tolerance earlier today. This is, we're going to blow right past that, but briefly touch on it. So the idea is that if you have multiple generals trying to attack Rome, this was the original thought experiment published by Leslie Lamport in 1982, about we can only communicate by messengers, and any of the messengers can be corrupted. And this is an extended allegory for the idea that you can have many nodes, and one of the nodes could be corrupted or could be an actual bad actor, and that you would want to figure out how to elect a leader in such a way that you have fault tolerance. And this idea of having a metastable way of dynamically electing a leader is the whole idea behind consensus mechanisms. How do we come to finding a leader who can tell us what the path forward is if you can't trust anyone? So historically, solutions in private that were put forward in order to solve this problem, DLS was named for Dwork, Lynch, and Stockmeyers, and this is the idea that you could have like part of the network come to sync, and then part of the network come to sync, and then those two pieces could talk to each other. We'll come back to this later because these concepts come up when we start talking about proof of stake. So in Lamport, Paxos, in 1990, released a paper in the first implementation of it. Paxos is like famously complicated and really confusing. It's the system that keeps your, database data store like massive Unix cluster. It's what keeps Zookeeper running.
Hey, Monica,
if you decide that, yeah.
Monica, can you turn off your video? Because some people are having audio problems.
Oh, sure. Yeah, let me turn off my video. How do I do that? Great. How about that? Is that better? I hope that's better because I'm just going to keep on cooking.
That's great. Keep going, Monica. Thank you.
Okay. Yeah. What were you talking about? Oh, Paxos. Very confusing. So if you decide that you get interested in the history of consensus protocols, try reading not the original Paxos paper, but Paxos Made Simple, which is the paper that Lamport released because his original paper was too confusing. So let's just blow through these, but the idea is that there were other solutions. PBFT, you'll hear come up later because it's implemented as part of Tendermint. Raft is a reworking of Paxos, and that's the one that keeps the cloud moving. So all of these concepts of coming to consensus in a private network, they're still in practice, and we keep iterating on them and bringing them back. So all of this research is still relevant and still stands today in all of these other implementations. So if historically we had all these ideas of how do we come to consensus in a trusted network or a semi-trusted network where you might have, I have a bunch of servers that are part of my business and I want to keep them talking to each other in a way that can survive some of them going down. Or we have a consortium of companies and we might want to figure out how to share data. We might have like a database of different nodes. And this is the idea behind having these consensus mechanisms in private. Then this totally new crazy thing came out, which is proof of work, and how it just totally blew open this idea of having a public consensus mechanism. So let's talk about Bitcoin. Bitcoin, 2008, the Nakamoto Bitcoin paper introduced a totally permissionless, and this was the new thing, permissionless economic BFT solution. So this is an idea that you could have your BFT consensus in a way where you didn't have to validate your nodes. You didn't have to know who was participating in your mechanism. And so it's a system for generating a log that assumes that it's synchronous, and it passes the proofs of past things forward into previous blocks, so Merkle proofs. And everybody's competing, the miners, in essentially a leader election. And the way that you get confirmed to be the leader is you produce a valid block, which means you solved the proof of work math problem. And Once you put forward a valid block, people check it, and you become the leader when people build on top of your chain. So it's a totally new way of solving the Byzantine general problem. The leader of the generals for the next round is just the one that has proven that. And the idea is that because you've done the work and you've contributed to the network, you care about the health of the network and you're not a bad actor. So Nakamoto consensus handles forking. So the idea that maybe Stu and I both have a correct solution at the same time. Stu and I just keep running, each with our own, and whichever chain becomes longer over time as people build on top of it, that's the one that becomes the successful fork. And if on the abandoned chain, the one that eventually loses, the miners get nothing if you've contributed to that chain, which provides incentive for people to switch as quickly as possible. Forking in Bitcoin really doesn't happen that often. And then as finality, the way that you come to consensus in Bitcoin, it's probabilistic. It's not like everybody votes in a round and then we all say, okay, it's block number 3. This idea of probabilistic depth is that it's likely that your chain becomes the real one because there's a lot of stuff built on top of you, and it's unlikely that your chain is going to be abandoned. So these concepts, solving a math problem probabilistically and then having that chain become buried, which makes it real. This is very different from the voting that we've seen come before. Bitcoin is stable. But the properties that make it stable, such as its fixed block size, fixed block time, and the longest chain fork choice rule, these also make it slow. Bitcoin doesn't have to be slow. It could have different features, but just the way that Bitcoin has the core devs and the maintainers and the creator of the system, they've chosen to have a 10-minute block time. They've chosen to have this particular way of doing confirmation. And it makes it strong and reliable, and that's just what Bitcoin is. But people have seen an opportunity to make variations on Bitcoin's proof of work. For example, Ethereum. Ethereum adopted the Ghost protocol, well, part of the Ghost protocol. And really, they implemented 2 really awesome features to blockchain. Probably many more, but at least 2. The 2 that I want to talk about, they have this distributed computation engine, the EVM, and this idea of having code on a blockchain. Very new, totally cracked open this whole world of smart contracts, which we are totally bought into, and Stu will talk about later. And they've also this idea of using the Ghost protocol to have uncle and orphan blocks. It allows you to have more references to blocks, which means that if you have more references, it's less likely that your chain will ever be abandoned, less likely. So you increase your confirmation time because it probabilistically increases your chain. So these innovations have made Ethereum much faster and more interesting for developers, but still suffers from throughput issues like, CryptoKitties getting popular, which is why the Ethereum devs are working on Casper, which we'll go into in a little bit. So there are many different proof of everything out there right now. We've got proof of stake, we've got changes to proof of work, we've got different kinds of proof of work, we've got proof of space and time, which we'll talk about in a little bit. And all of these different variations are all looking to improve on what we've got now, this world of Bitcoin and Ethereum and proof of work, and taking it to a place where we can have more throughput, more scalability, and better smart contracts. So what's going on now, and how can we think about them in a way that intelligently acknowledges the work that's come before and how we're using it? That'll give us a framework to see the potential benefits and drawbacks of all the different kinds of protocols. So not going to talk about red herring things that are non-BFT economic. They're still interesting. They still provide a way for everybody to eventually come to consensus, but they're just not within the scope. So things that are like proof of stuff, where you have to have an oracle of attestation of some external piece of data that you use on the chain, like Orbs project and Cardano that does the like closing off epochs and having to come in to consensus again, and NEM. We're not going to talk about them. We're going to like briefly blow through them, but deterministic projects will go through proof of stake, Casper, Tendermint, what's the difference between DPoS and federated, and there's some EO stuff in there. And then probabilistic, we'll talk about Chia and then a little bit of our own project. And then you can ask questions about that if you're interested. So let's do it. Non-economic BFT. So in this case, by that, I mean that there's no built-in economic way of automating Byzantine fault-tolerant, resistant consensus. So this is like a reputation, just like not on the block, like you 5-star each other and then your reputation becomes a mechanism. There are projects looking to put that on the blockchain. They're not a consensus protocol in terms of BFT, like Byzantine fault tolerance. NEM is not either. Like, we can talk about Cardano, but in my opinion, it's also not a economic BFT way of doing consensus. And then validation projects that are use the term proof of, like proof of location or proof of age. These are also not consensus protocols. But things that are consensus protocols, proof of stake was originally introduced in a paper in 2020, and it takes these ideas back from Raft and Paxos and this idea of voting and generals that might want to vote each other in and out of power, and said proof of work is great. We love having a public network where everybody participate regardless of the trust level, but we don't like mining because mining takes too much energy, and also Bitcoin is slow. So we're going to take this technology that we've already had and figure out how to roll it out in a way that it's sustainable on a public network. But these systems were not originally designed to survive in a trustless environment. This idea that anybody can just spin up a GPU in their closet in order to participate in a network, you have to then deal with some problems that arise because they might just be coming to troll you with your network because lulls on the internet. So this idea that you might want to stake some value in the network in order to vote, there's some issues with it that people that are working on proof of stake projects are coming up with mechanisms to solve. Issues are nothing at stake. So this is, if you generate a block and then you have to vote on things, you could vote on multiple histories because you don't really care because you're not staking anything. A long range attack is where somebody does and then they pull their stake out, but then still try to do changes to things. And then tragedy of the commons is one where if you have lots of people voting, then voter participation is really hard to maintain. And if everybody has a vote and they feel like their votes don't really count or matter, it becomes really cheap to start to bribe the voters. So proof of stake, by going back to this original voting technology in Raft and Paxos, brings back some of these theories, these issues that they're trying to solve through game theory. So Casper, the TFG version, this is the correct by construction version that Vlad and his team are working on at Ethereum. This is, it doesn't just take uncle blocks from Ghost, it uses the whole greediest subtree. And then in addition to that, the only staked validators are participating. So that's a way of getting around the nothing at stake problem. They use check the liveness of a security deposit to solve the long range issues, slash people that have bad actors, and then they rotate who's participating so that the network doesn't get stale. Tendermint is really interesting because it actually goes back to PBFT and tries to combine that with proof of stake. It uses the same leader election from PBFT's rotating leaders, but then it uses Merkle proofs to link blocks together like a blockchain does. And it uses slashing sort of like Casper does in order to, if you stake something and then you vote for something that turns out to be bad, they'll cut your staking, they'll punish you for it. And then Tendermint has made the choice to choose to be available rather than necessarily consistent. So this is they've made the choice where the network is always going to be up and you can keep publishing transactions, but there might be moments in time where the network is actually not consistent and you have to wait for it to like figure itself out. And this is because Tendermint prioritizes being alive for everybody to be able to constantly access it.
5 minutes.
Different projects have made different choices.
5 minutes. Mom.
Oh, 5 minutes. All right, I'm keep going. Delegated and federated systems. Whew, NEO, delegated BFT. So this is the idea that you want to elect a bunch of bookkeepers, and then some subset of your bookkeepers will agree. This means that the number of people that are validators is actually very small. NEO has a very small number of nodes. And node holders, they actually have to like tell the government who they are. And unlike they're doing the opposite of Tendermint, they want safety first. So if there's a problem in terms of consensus, they actually stop the network. BitShares and EOS are using DPoS, so this is delegated proof of stake. It's like the inverse of NEO. Instead of having a small number of bookkeepers and they all agree on what goes in every block, it's more witnesses and every witness produces their own block. So the issue with this is that people have to vote to elect the witnesses. But voter participation is really hard to maintain. And you have the bribery issue of tragedy of the commons. And you might also have the issue where the people that actually holding the currency, maybe for speculation, are the validators, but the people that actually use the network want to keep the price low, but speculators want to keep the price high. So there's a misalignment of incentives between users of the network and owners of the network. Ripple and Stellar are using a federated Byzantine agreement system, which is actually not BFT. It's a series of overlapping independent BFTs that each individually come to consensus and then they go back and talk to each other. This is a hallmark back to DLS, which is, you know, super old school, but now we're trying to roll it out in a totally different way for a trustless network. All right, all right, we're done with the deterministic protocols. Non-deterministic, Chia. Chia is doing proof of space and time. It's really interesting. You should totally check out their stuff. But briefly, the idea is that you want to pre-compute a bunch of calculations that are really time-consuming and store them on a disk. And then when you say that you want to be a validator and approve something, then you would actually show the result of one of these computations in an amount of time that's much less than the amount of time it would have taken to compute, which is how you prove that you have all that volume storage stashed away. So I think that's a really interesting take. They're promoting it as green because it doesn't require real-time computation. Check it out. Bram Cohen is brilliant. She is cool. And briefly talk about our own project, which is called ChainWeb. ChainWeb is many braided Bitcoin-like Nakamoto consensus chains that all pass their Merkle proofs to each other. And based on the graph structure, you can propagate the information really quickly out to the. And because of the different references, you get the same protocol because you have all of these extra block references, which decrease confirmation time. But unlike Ghost, the blocks that you're referencing aren't like uncle blocks that are not containing real information. They're still real blocks. Yeah, so that's our project and a brief overview of many different types of consensus protocols. I hope that going back at these slides will be helpful when you're thinking about different projects. Stu, how did I do?
You're doing good.
Yeah, thank you, Monica. It's very helpful.
Do we have questions?
Let's see. How did you guys want to organize this? Did you want to take questions from Monica now, or did Stuart want to give a talk now?
Yeah, let's do.
Okay, great. Well, I can go ahead and read you some of the questions. So we've got a question from Jay Berg in the audience, and Jay asks, let's see, proof of skill, proof of stake, where the stake is received from the skill of predicting public sporting events. Okay, that sounds like another interesting Oracle-based process, or like it's data that's providing some sort of trusted information. So seems sort of like proof of reputation, like proof of reputation of I'm a really great Lyft passenger.
it's not really different from that idea in that proof of being good at predicting sporting events. So sounds cool. Are you saying mining in the future won't exist or will be less used? I think that mining in the future, we just want to make it more effective and more efficient. I think that the whole issue with Bitcoin right now, if we could just produce transaction volume using the same hash power of Bitcoin, but do it at like 10,000 transactions per second, that nobody would be worrying about mining from an ecological standpoint because we would be getting a lot of value from it. We'd just be thinking about how to make it sustainable. So I think we're still going to need mining because proof of work is just a really beautiful way to come to public consensus without having to do complicated game theory things. I think we're just going to be using mining in a more efficient way. Could you provide more insights on the effectiveness of Kadena governance model or your take on on-chain or off-chain governance models? So this is, maybe I should actually kick this question to Stu, because the way that Kadena handles governance is actually inside of the smart contract layer. So I'm going to punt on this question and send it to Stu. But cloud dev, we have not forgotten about you. There is a question, what is slashing? I talked about slashing, but briefly, it's the idea that if you stake something and then you vote for something that was actually determined to be a bad block, that your stake gets cut. And it's a way of punishing people that are bad actors in the system. Your approach to ChainWeb is that the solution to scalability is proof of work. Yes. Same idea as question number 2, which was that we're not going to have mining anymore. I think we're going to have mining. We're just going to mine in a much more efficient way. So ChainWeb is a way to spread your hash power in a much more effective way to publish many blocks all at the same time. Yeah, I think I'm mostly out of time.
All right.
Yeah.
Okay.
Stu, do you want to go for it?
Insightful. We really appreciate your presentation. We learned a lot, and very, very helpful. In fact, I think you clarified a lot of the confusion that the audience had about all these different alternatives that may have been coming up through the summit. So you've done a very good service for our audience. So thank you for that. Stuart, would you like to continue with your presentation?
I'm glad to be here.
Sure. Let me turn off my AC so it's not so noisy. All right, can everyone see the presentation? Yeah.
Yep, looks great.
Okay. So hi again, I'm Stuart Popejoy. I'm going to be talking about some concepts in smart contracts with, obviously, this is going to be a little more focused on our technology, which is called Pact. And we're calling this advanced smart contracts. So the idea here is that we're not going to be going into a lot of questions about what smart contracts are, as much as we're going to be kind of jumping right into some concepts of like what we really need to make smart contracts, into the kind of get the power from them that we're really looking for in blockchain systems. So one of the things that I think everybody agrees about smart contracts is that they need to be safe. The idea is that you're basically throwing code onto a blockchain that can spend money. And the idea there is that you can think of it as automating processes, which is something that computers have done forever. But now we're doing it with live ammo, in the sense that even like a shopping cart application at the end of the day is just going to send a message over to your credit card company. And that's not a deterministic confirmation, and there's a bunch of trust involved. There's basically points along the way for, not just then, but weeks after, where people can reverse transactions, which is actually a feature, because that way errors can be corrected, fraud can be detected, all these kinds of things. Whereas on a blockchain, the money changes hands immediately. So if you have a bug, it can be catastrophic. Ethereum, obviously, as many know, has had numerous bugs and exploits with costs in the millions. And the hundreds of millions. The other thing to keep in mind with, and it's a general concept in software development, and it's even more true in smart contracts, is that developers are not superheroes. You can't expect developers to just get better and better and better and anticipate all the exploits that might come out of a system that's fundamentally unsafe. Lastly, one thing is that tests and the concept of testing a smart contract, in the sense that you're going to write a bunch of tests that exercise your smart contract, and that's how you're going to prevent bugs from happening, is widely seen as not being enough, because you can only, we'll get into why that's true, but these are just some of the safety issues in smart contracts. The other thing that we really want smart contracts to be are simple. And what does simple mean? So simple means that the smart contract is easy to understand, in the sense that you should understand what the smart contract is doing, you should understand what its purpose is, and ideally the code, you should be able to look at the code to make, to figure that out. Simple has other benefits. It means that it's faster to code. So this is something where, right now, if you have a system that's very unsafe, you're going to approach it in a very trepidatious fashion, in a very cautious fashion, and it's going to mean that it's going to take you a long time to write your code. Most importantly, simple means safer, and the reason why it's safer is that simple generally, a concept of simple can kind of mean smaller, in the sense that there's less code. With less code, there's kind of less places for bugs to hide. A concept that doesn't come up very often is the idea that simple means that other stakeholders can understand it. And what do we mean by other stakeholders? If you have a smart contract, that smart contract kind of represents what your business is doing, and it basically encodes your business's processes and logic onto the blockchain. At that point, you can imagine that it's not just the developers who care what the smart contract is doing. Wouldn't it be great if your business users, or even your lawyers, or anybody else in your team could look at the code and have a hope of understanding what's going on? The last thing about smart contracts is that we want them to be maintainable. The first concept here is that upgrades are essential. So Ethereum is classically, you can't upgrade a smart contract. Now, of course, there are ways to introduce an upgradable framework over Ethereum, but essentially you deploy a smart contract to an address, and eventually you're going to be calling code at that address, and that address can never be changed. Data migration is very essential. So the idea here is that if you're going to introduce, at some point you're going to want to upgrade your smart contract, and that might mean that you also want to be able to upgrade the data that it holds. This is a bog standard concept in software engineering everywhere else, but it's not really available it requires a lot of advanced engineering to be able to handle something like this in a platform like Ethereum. Lastly, you need, one of the most important things you need is per contract governance. So governance means a lot of different things in blockchain. Governance can refer to how hard forks are administered. That's kind of where Tezos is focused. Governance can refer to just kind of like nitty-gritty of consensus issues. With smart contracts, what we like to think of is that when you roll out your smart contract, you can design a governance protocol that says how the code can be changed and how the data can be managed. And then the last thing is that contracts need to be interoperable. And while this seems like a tautology or something where, well, isn't that obvious? We have a situation today in Ethereum where it's very difficult for contracts to actually work with each other, in the sense that it's one thing to have a contract that can work with an ERC20, because everybody knows what an ERC20 is, but it's much more difficult for contracts to work with kind of other bespoke contracts. And we really don't see very much of it on Ethereum. Why is this important? Because part of maintainability is factoring and being able to reuse components. And that's not just about code, that's actually about having services and being able to reuse services on a blockchain. So that's kind of what we're saying are some of the things that we need to have truly advanced smart contracts. So what we are focused on at Cadena is solving some of these problems. And one of the most powerful tools for having safe smart contracts is the ability to do something called formal verification. before we say what formal verification is, what formal verification seeks to augment or even replace is the concept of testing. So testing, when you have a smart contract, you can only test what you know, and this is the big problem with tests. Developers who write the test must think of every scenario that could ever possibly happen, and of course that means that there's going to be any number of corner cases or scenarios that they didn't think of, because developers have a tendency to, test the design they built and not think about ways that, like, someone who has a different design in mind might kind of like hack their system or something like that. There are other techniques that are out there that that are in use in software development today, like fuzzers, which are the kind of things that try to basically throw, and quick check. These are things that basically throw random inputs at your code. And these are extremely helpful, but it's important to realize that they're basically probabilistic, in the sense that they're going to use probability to try to give you some sense of confidence that every kind of bad scenario in your code has been tested. So, so enter formal verification, which is basically the idea that you're going to try to get the computer to prove to you that your code doesn't have bugs. The thing about using a theorem prover is that it can be very difficult. And so I'm going to contrast what I'm calling hard mode or expert mode and using a theorem prover in an easy way. In the hard mode, for starters, whatever the environment you're trying to test has to have a full specification and basically be entirely simulated within the prover environment. That's an effort that can take years. For instance, Ethereum finally, it took over a year for the Ethereum EVM to be represented in Hall and Isabelle. And that doesn't do anything to get you closer to being able to test Solidity scripts. What's more, the proofs at that point have to be written in the prover tools dialect, which basically requires a PhD in these kinds of techniques. And so the code I put here is an example from Cook. It's something where you have to understand all sorts of things about formal logic, and you need to be able to look at something like this and be like, oh yeah, no duh. X, Y, and Z is happening here. And for the rest of us, we look at something like this and to say, I have no idea what's going on. So what is it? Is there such thing as an easy mode for a theorem prover? What we have done, basically what I'm talking about here is what we've done in Pact, which is we've implemented a form of model checking, which is where you have the code that you're trying to prove things about, and you instrument that code with small proofs that kind of represent things that you're motivated to prove as true. And the important thing there is that there needs to be a domain-specific language, a DSL, that is easy to read and write, so that you don't need a PhD to be able to do these things. And then lastly, it needs to be a little motivated about what you're trying to prove. We're on a blockchain, and a lot of the biggest concern is that we're going to end up writing state to the blockchain that's incorrect. And then the other thing that's probably very important is be able to make sure that we're authorizing access correctly to various resources. So I'm going to just show a little of what this looks like, which means I need to, what do I do here? I go back here and how do I do this? Oh, there's the X. Okay, sorry. Let me just change here to this screen. Okay, so here, so this is some Pact code, and the idea that what we're looking at here is an accounts, a module called accounts. So smart contracts in Pact are called modules, and the code here is basically designed to give you the ability to, transfer funds from person A to person B. So here's an example function where you want to be able to transfer from a source account to a destination account some amount. What we're looking at here is the recent support for formal verification in Pact. So without formal verification, what you end up with is kind of typical code. So we have the notion of schemas in Pact, and we have the notion of tables. So the idea is that the thing that we're storing in the blockchain is a simple ledger where we have the balance, we have whatever amount was updated, and we have the currency. The idea here is that we can now instrument this code with what's called an invariant. And so what this invariant does is it says that at any point in time when the table that stores these accounts in it, the balance can never drop below 0. And so that seems like a fairly straightforward thing. But what's interesting about this is that we can now have all of the, because it's defined on the table as opposed to defined on a function, we can now say that all of the if this code does not produce any errors, we can say that this invariant is never false, and this is a bug we will never encounter. So how do we know that this is actually working? Well, the easiest way to check is let's put in an invariant that kind of doesn't make sense. So let's say that we want to say that the balance is always greater than 1 unit or $1. If we save that, what's going to happen is we're going to get error messages from the system that show us all the places where this invariant could be false. So, for instance, in transfer, what it's doing is the system behind the scenes is basically searching the entire space of possible inputs to say what is an amount that would invalidate this model. And obviously, since we've said that the balance must be $1, the only thing we need is for someone to transfer $1 to someone else with a balance that is at $1. So now, if we go back and fix that, all these errors go away. The other way to see things happening is, since we've said that the balance has to always be greater than 0, say we had some kind of bug where we subtracted, we initialized something with negative, with a negative $1. Now we'll see that immediately this pops up with an error where it said, that's a really obvious one because when we create an initial account, obviously the balance is less than 0. So it just pops up like that. And what's important to note is we didn't have to write any tests to do this. All we had to do is specify this invariant, and the code basically finds the bugs for us. The other example I wanted to show is, that's what's called an invariant. The other example I wanted to show was what's called a property. So we, in this example here, I just want to see what, I'm using the sample code for this. Yeah, so we have a property here. This is a very interesting property that is available in our system. And again, the idea here is that we have a very kind of stylized system that allows you to say things that are kind of valuable in a blockchain context. So one idea here is that we can say that that the accounts table, so this idea of a column delta is to say what kind of changes to the sum of of all the values in a table in a particular account, and in this case, the balance column, what kind of changes are possible. And in this case, we want to say that those changes always have to sum to 0. And so this is basically double spend. So the idea is that if the debit or the credit function that these things call had a bug where, for instance, we did some bad math, you'll see the error pop up right here that and it's basically giving you the inputs you need to invalidate the property that was defined up here. And just so you know, this feature is basically in beta. This is in the packed version that is out and available to the public. That's what I'm using to demo to you. One of the things we're working on is making these error messages a little more intuitive right now. These are showing you the values that come into the transfer function. And it's showing you, with the current scenario, it's showing you a value for amount, which is this S2. You pass 1 into that, and you will end up with a bug because then at that point you go stare at your code and try and figure out what you screwed up. In this case, it's that debit should have subtracted balance and amount instead of added it. And then now we see all our errors go away. So again, this is just a quick demo of a very powerful new feature that we have in the Pack Smart Contract language. So let me bring back my window here, because that's just going to be the quickest way to see if I can do that. Sorry, I'm going to go back to my talk real quick here. So why won't it let me? One second. Why won't it let me do that? Let's see. Okie dokie. All right, I'm going to have to close my Atom window. Sorry for the delay here. Wow, I just don't really know what's going on with Chrome. Close that. See if we can get back to, I don't know where my window went. All right, sorry, folks. All right, let me just put this in here. Paste. And get back to the talk. Chrome tab. All right, let's make sure we can see this. So hopefully,
Great, keep going.
Okay, so, sorry about the delay there. So that was a little demo of our formal verification system. So just wanted to go through a couple other topics. So governance and maintainability, which we think are related notions in smart contracts. Maintaining code on the blockchain. So one of the things is obviously, you know, it's a fairly naive idea to think that, or it's an extremely naive idea to think that the first iteration of your code that you throw on the blockchain is going to work just exactly as you planned. So the first thing you have to be able to do is be able to upgrade your code. That's an essential feature for maintainability. You also need to be able to migrate data. This isn't, the idea being here is that you got things stored on the blockchain. So the idea is that when you want to offer new features to people, you might need to be able to mutate that data that's on there so that you can offer new features to people. It's also a critical issue when you're trying to solve an exploit. An interesting thing about maintainability and about upgrading is that it requires a name or a directory-based approach, which Ethereum has a name service now, ENS, but it's important to realize that this is a layer above this is again another layer that's well above the actual blockchain layer itself. But that's not to say that it's not a good thing. The Ethereum name service is actually a very needed thing, and it's the kind of thing that we're going to see more of as we move forward with smart contracts. And lastly, it requires governance. The idea being that if you're going to be able to upgrade, you got to make sure that not just anybody can upgrade your code. So what governance looks like in Pact today, and this was true from Pact 1.0 when we rolled out Pact 2 years ago to private blockchain clients, is that the governance is public key cryptography based. And one of the things, like all of Pact, is that it's multi-sig friendly out of the box. So with something like a code upgrade, it makes a lot of sense to not just have that one developer who's got that one public key. And so if he goes on vacation, he or she goes on vacation, you won't be able to upgrade your code. I mean, so the other thing is that once you have basically identified yourself and signed a transaction with the proper signatures, at that point you can directly upgrade the code and you can directly manipulate the data. And we have a small example here. Let's say we have a smart contract called inventory. The idea here is that when you define a module in Pact, the very next thing you do is specify a rule that has to do with public keys. And that could just be a single public key, or it could be multiple public key. And that rule could say that, like, best 2 out of 5, you know, or not best 2 out of 5, but, you know, that you have 5 signatures and at least 3 people must sign the transaction that doesn't upgrade. And, you know, the rest of this is just to say, you know, that you have things like schemas and tables. And so the idea being is that once you have a transaction that, normally in Pact, once you define a module and you define a table, normal users cannot directly write to that table. They have to call functions in your module to be able to get to the data in that table, which means you control access to your table. However, if you come in and you've signed with the admin's key set, you can directly issue, write, update, insert, all these kinds of database operations right within that transaction and directly mutate data, which is important when you're trying to do upgrades and handle exploits. Now, where governance is going in Pact is a relatively small change, which is to move to a model that allows fully general governance. And this is, when I say tomorrow, I mean like literally the next version of Pact. We released a version of Pact last month, so this next one should be coming out late this month. And what this does is, as opposed to the other one where you have this little tick here that lets you know that this is a name and that's specifying a key set. Now you just have a symbol that basically refers to a function inside of your module. And so what can you do with generalized governance? You can do more decentralized governance. So for instance, you could collect votes based on user population, and you could present like 3 different upgrades and people could vote on the one they like best. And the way you identified upgrades is by the hash of the transaction that's coming in. So interestingly enough, if you had a function called tally votes, which is basically going into your database and seeing all the votes that are recorded, when it comes time to actually perform the somebody wins those votes, they come in and actually perform. All this function has to do is check the votes for the current transaction hash. That's what this is, actually a function call here that is returning the hash of the inbound transaction. And that's really all a decentralized governance mechanism would have to do. The other thing you can do is key sets right now implement kind of basic multi-sig schemes. If you wanted to do something where you wanted to have like a kind of composite model where maybe you have votes, but you also have a board of directors, and like you have to have 1 out of 5 of the board of directors, and you have to have votes. That's the kind of thing that you could implement in the generalized governance scheme. So the last part of this talk, and I know we're running low on time, so is to talk about safety in smart contracts and come back to Ethereum and how hard it is to write safe code in Ethereum. One of the reasons why is that the EVM is a fully general machine model, in the sense that there's no notions of safety in terms of, like, for instance, you could jump to addresses that don't exist. There's no notion of like type safety, like is that a string you're looking at? Is that a Boolean value? Not to mention that the way the EVM works is you basically run the contract and see what happens. There's no, the agreed upon point of entry for all EVM contracts is basically the first instruction. And that's what gets run every single time. It doesn't matter what you send in, what kind of transaction you send to a smart contract in EVM, it's always going to just fire up the contract. And so in the case of Solidity, that's going to do something. The first thing it's going to do is dispatch to the right function definition. But what it means is it's just a very opaque and kind of unsafe model at the lowest level. Kind of shockingly, there's no multi-sig support in Ethereum. Ethereum is a fundamentally single signature engine, which means that when developers want to do multi-sig, they actually have to run, they have to do kind of like the way you gather votes or something like that, in the sense that they'd have to collect signatures over multiple transactions, or even worse, implement signature checking in smart contract code, which is very gas intensive. What this all adds up to, of course, is extremely slow development time while developers worry about all these things. So the idea behind Pact was that it was safe by design. An example of this, and what we're talking about here are some of the things that make it where we're trying to kind of constrain what programmers can do. So one of the things we don't have in Pact is recursion. A function can't call itself. This is recursion, while useful, is a very clear source of bugs in almost every system. And mind you, we do have iteration. It's just we don't have recursion. We don't have functions that can call themselves, but you can iterate over a list structure, over an object structure, or anything like that. The DAO bug, the famous DAO bug that where 50 million ether was stolen, was caused by a recursion bug. It's SQL-like instead of object-oriented-like. And that's nice because there's certain things, there's certain bugs that can happen. For instance, when you rename a contract, there's a bug in a contract called Rubixi where they renamed the contract, but they didn't rename the constructor, which is kind of a magic method that shows up in object-oriented. Not to mention inheritance causes all sorts of bugs. And lastly, anytime if you do import another contract, like you call another contract inside of yours, that code all gets hard inlined into your code, so it can never break. This allows us to avoid a whole category of bugs that was most recently seen in the parity wallet bug, where contracts were calling another contract that had kind of the master code for all wallets. That contract got deleted, and then all of a sudden, something like $200 million worth of Ethereum got locked up and is still locked up to this day. It's been locked up for months. But the other side of safety is actually means that things are easier and faster, because a lot of times people look at safety and they think, oh, it's all these ways that it's going to lock down and make my life miserable. It's actually makes your life better. So the first one is that there's more built-in functionality in Pact than there is in the EVM, which has barely anything. Obviously, EVM is a very low-level system, which means that Solidity is providing a lot of that, but you have to basically write a lot of code yourself. Pact has a standard library. This is that, and it as an interpreted language, it has to have this. So there's lots of utility that you can use right out of the box. Another thing we have is multi-step transactions. This was something that I wanted to do a demo of, but I think we're probably not going to have time. How easy it is to orchestrate something like a two-party escrow multi-step transaction. These are the kind of things that are very hard to get right if you're writing them from just raw code. But in Pact, you write this thing called a pact, and you say step 1 is this, step 2 is this, and all of a sudden a bunch of bugs disappear because step 1 can only lead to step 2. A programmer doesn't have to verify that, the language enforces it. As we mentioned before, multi-sig support is built in, so you don't have to build that. And finally, there's just a nice, easy-to-use database model, which at the end of the day is easier especially for business customers. Things are easier when you can just talk about things being modeled in a key value database. So looking at the time, I think we're kind of out of time, so I don't think I'm. But this is just, at least we can look at this code briefly of a pact.
You have a few more minutes here. Because you started a little bit late, so feel free to complete your presentation. Okay.
So this is an example of code that implements a two-party escrow. And obviously not everything is here, and we'll actually go look at some of the definitions of this code just to give you an idea of what's going on. But the idea here is that when you design a pact, you basically just say you design these things called steps, and at that point, the arguments that you pass into this pact are basically form the environment, the kind of read-only environment that all the steps run into. So the idea is that if you're doing two-party escrow, you have a debitor account, you have a creditor account, you have the initial escrow amount, and you have a timeout. And this basically gives you all the parameters you need to basically initiate an escrow. So what happens here? There's two steps. We have this concept of a step with rollback, and the idea here is that this is a cancelable step. So this is very important, obviously, because the whole point of escrow is you want to have a way to get out of the escrow if something goes wrong midstream. And then you have a second step, which is everything's gone fine. We're ready to kind of like seal the deal. So what we're doing here is we're just calling functions. Initialize escrow, all it really needs is the escrow amount in the debitor account, because all init escrow is going to do is put the money into a safe place. Now, that's where this gets interesting. So the two things we're going to look at right now are init escrow, and we're going to look at cancel escrow. So let's see if I can pull this off quickly enough here. Not sure. Yeah, there we go. So I'm going to, is it going to let me share a screen? I don't know why it's not. Oh, there we go. Screen 2. And let's go to Atom. And let's open, sorry. This is why I wasn't sure I'd have time. Let's just reopen what we were just looking at here. Hopefully it will open. I was having problems with Atom earlier. It being very slow while this thing's running. Yeah, I don't know we're going to actually be able to. All we were really going to do is look. I'll actually just kind of take you through the code just quickly. So the interesting thing about packs, so in addition to making it very easy for you to orchestrate these kinds of things, is that, so what would happen in a NIT escrow is, the question is, where does the money go? So the idea is that the person who's buying something needs to escrow their money, and an interesting thing that packs offer is what is called a packed account. So basically at this point, you're handing the transaction money, and it becomes a trustless kind of decentralized place where the money sits, and it's governed by the code at that point. So nobody can get to that money except the people who are participating in this particular pact. So when you run a pact, like if I'm selling a TV to Monica, and I start one of these things off, or Monica's selling a TV to me, and I start it off to escrow my account, that gets a ID for that multi-step transaction, and the money basically gets associated forever with that ID until something happens to move the money somewhere else. So in cancel escrow, what we are doing at that point is that we have rules that say who can cancel this and when. So the idea is that we're saying what the timeout is, we're saying that it's we're passing both the accounts to there, and we're saying what the escrow amount is. So the idea is that up to like a week, as the person who escrowed the money, I can't cancel the code. So I can't cancel the transaction. But after a week, if Monica's run off with the TV, then I can go ahead and go in and get my money back. Meanwhile, Monica can cancel the transaction at any time. If she's the person who signed this transaction, then she can go in and cancel, and then the money gets refunded. So the last part is finishing the escrow, and that is something where we want a multi-sig, and we allow for the price to be negotiated. So Monica brought over the TV. It's got a little ding in it. Monica's like, fine, I'll take 10 bucks off of it. And so we negotiate a price. I get refunded the 10 bucks, and the remainder, let's say it was 200 bucks that originally went into escrow, goes over to Monica's account, and necessarily we both had to sign that. Now, the thing to realize is that what we've avoided with this is that we've avoided needing to have the kind of classic third party that you need usually in escrow by having this trustless structure by which you can actually associate money with a running packed instance. So this is the kind of thing that, unfortunately, I wasn't able to show you the functions, but this is the kind of thing that if you tried to code this from scratch, you'd be spending an awful long time doing this. Whereas because of the pack structure and the ability to kind of store money with a running packed ID as a built-in language feature, there are some very powerful use cases that can be built out of this, including like where we're looking at it is for insurance-linked securities and all sorts of kind of syndication and kind of payment flows scenarios. So, all right, so that's it. This talk is available here. Maybe we can get the folks here to send this out. If you want to look more, learn more about Pact, you can go to our web editor, which is interesting because that's someplace where you can just start playing with Pact right in the browser. You can start programming around with this. Actually loads this hello world smart contract, so I can say hello hack summit, and look, it comes right out. So this is a nice place for you to be able to play with Pact. You should check that out. You should also go check out our GitHub. Finally, if you want to find this talk, this is where it's at. So thanks so much, and I guess we'll take some questions if we have time.
Awesome, thank you, Stuart. Why don't you leave the slide up so that people can just have it up instead of so continue to share your screen. That way people have this and they can see those links. While
okay. And
I'll read the questions to you, by the way.
Oh, okay, that's fine. Okay, so I'll just read this. Okay.
So just go ahead and reshare that page. That way people can take action from here. Okay. So there's a question that Monica brought up earlier that she thought should be tossed to you, which is, could you provide more insights onto the effectiveness of the Cadena governance model, or your take on-chain or off-chain governance models? Governance in the crypto space is a very hard problem. On-chain and off-chain governance models come with a host of problems. Any thoughts on that, Stu?
I think on-chain is, so I think the question is probably, so we talked about governance in a per smart contract level, honestly solves at least a lot of the problems that we've seen with Ethereum, at least with respect to things like the DAO hack. if they had just been able to fix that bug and they had a decent like governance mechanism in place, they would have never, we wouldn't have ETH Classic and ETH today. So it's important to, anytime you're thinking about these kinds of problems, it's important to be very specific about looking at the kinds of things that might have caused a governance issue. On a smart contract system, you're going to want per smart contract governance. That's going to be important for that to be built in, because you're going to, otherwise you're in a situation like with Ethereum, you know, where Ethereum has been asked to hard fork again, and indeed for the Parity wallet, they're looking at doing some kind of like soft fork where they put in, you know, but again, this is like invoking the authority of the kind of like core devs. So otherwise though, we're talking about things like, you know, hard forks and, you know, being able to make changes to the protocol itself. Certainly in ChainWeb, we're just going with the hard fork model. You know, there's no question that, which is basically off-chain. There's no question that off-chain can be difficult. It's hurting cats. You know, you have to deal with the fact that some people have more influence than others. It's been criticized even as by Angela Walsh and other kind of like astute observers who say that this is going to be a major issue if governments ever want to issue cryptocurrencies. The fact that you basically have kind of a dictatorship in, but you know, but it's an informal dictatorship where, you know, basically people have kind of a pulpit by which they can say, like the core devs of Bitcoin. On-chain, I think, is extremely thorny, and that's what Tezos set out to implement. And without going into it too much, because it's actually been a while since I was kind of having these arguments in earnest. It was more like last summer. The problem is, of course, is that you're doing something on chain that will then be affected by something that's fundamentally kind of external to a chain process, which is a hard fork. When you consider what a hard fork can do, a hard fork can change the protocol software. A hard fork can change all the data in the blockchain. So you're going to build something into your blockchain that could be changed by a hard fork. So there's so while it might seem attractive to be able to kind of host, it's basically trying to kind of host the community process on the chain. We do feel like that things like protocol changes are fundamentally off-chain. And indeed, in ChainWeb, one of the things about ChainWeb, of an example of something that cannot be dynamically changed, is the size of the network in ChainWeb, which directly determines throughput. So if we launch ChainWeb with 200 chains, which gets us, you know, something like 2,000 transactions per second, and we start running out of throughput, or you know, we start running out of capacity, we would then change the network layout, but that requires a hard fork to introduce new chains. So at that point, we would hard fork to 500 or 1,000 chains. But we foresee this as a fairly straightforward process where everybody should be in line with it, because more bandwidth, more availability is something that benefits everybody in the system.
Great, thank you, Stuart. So we're just about out of time here, but if you wanted to ask Stuart additional questions, or if your question didn't get answered today, you can feel free to email him at the email address you see here. And Stuart, you can feel free to jump into the chat as well and to chat with the audience if you wanted to answer questions there as well. Okay. But I just want to acknowledge both you and Monica for being here, and William, who couldn't be here today. You've taught us all just a ton about consensus, and the packed programming language is fantastic. So, you know, we're really inspired and we learned a lot. And I just want to thank you for being so generous and taking the time to be here today.
Thank you.
Back with the CEO of NewCipher, who's creating a proxy re-encryption layer for the blockchain. And it's going to be a whole new paradigm that we can learn about. So just hang in there. Be right back. And thanks again, Stu and Monica.
Thank you.